Hi. So it is the buzzwordiest title. Right, just to be clear about that. I'm glad you're all here on Team Jeff with me. First, just a little bit about our use case at iRobot. We make physical things that you buy. And one of the things about that, right, is that you pay us once and never again. But if it's using the cloud, right, you've connected it to the internet, we're paying for that throughout time, which means that we're very cost conscious. And that means the better that our mechanical and electrical engineers do their jobs, the more the cloud costs us. And at our volumes, a penny off the cost of a robot is tens of thousands of dollars. So yeah, that drives a lot of the decisions I'm going to talk about in our architecture. So first, how and why did we choose serverless? I'm not really going to cover the why. I think we all know why. That's why we're here. But the how is that we were migrating to AWS, that we had a previous IoT cloud provider that we were using that wasn't working out for us for a few reasons, including scaling, and we decided to migrate to a different platform. And so it involved two things. One, moving the contact layer, which is what the robots and apps use to communicate with the cloud, as well as the backend. So the communication layer was moved from our IoT cloud provider to AWS IoT, which I'll be talking about at reInvent. And our backend was moved from a combination of scripting on the cloud provider and some Azure and some on-prem data warehousing, and that was all shifted into AWS. So the combination of these things meant that we had pure greenfield development, right? We were able to choose exactly how we wanted to do this, how we wanted to implement it. So then it became a question of what does our architecture look like? Is it really sort of monolithic or is it microservices? And I think, the answer is once you're doing functions as a deployment unit of deployment, you kind of are inherently having a microservice architecture. But I think it's of value to step back and look at why we really choose microservices. So you're separating code into small units, which makes it easier to understand, maintain, and test. It also helps when you have these small units, it makes deployment easier. So that's sort of an ops benefit. There's also an organizational benefit, right? That if your teams are more decoupled, that there are fewer meetings. And that's especially true if your teams both build and run the services, which at iRobot, we don't do that. We have a separate ops team that closely collaborates with engineering. It's still sort of a DevOps process, but isn't quite fully into each team owns entirely the end-to-end piece. So now that we're on microservices, the question is how do you actually architect the individual microservices? And the traditional answer is that you use RPC of some type, usually HTTP, but there's gRPC and all sorts of others. You might even use a message bus or something. But when you're serverless, it's usually on AWS, API gateway, or whatever the equivalent is on your platform. And there are implications that come along with this. And I want to talk about what those implications are and why we chose not to use API gateway as the interface between our microservices. So these are the sort of topics. I'm going to look at it from a latency, cost, deployment, discovery, and security perspective. So first, latency and cost, which when you're serverless is really, they're one and the same, right? If you're not paying for idle, then however much latency you're inducing is your cost. If you're on a traditional architecture, then even high latency services, if you're using some async IO library or system, you don't have to pay for services that are just sitting around waiting. There's not much overhead in having that just running on an instance that you already paid for. So here's an example of a service, a very simple one, where it's really just wrapping a database. For us, the best example of this is our association service, which maps the connections between users and robots. And so that's a permissioning piece. So basically every call that the user is making touches this service. When you say, I want to know what my robot has done in the last 30 days, it asks, do you have permission to talk to that robot? And so really it's just a DynamoDB table, but there's some KMS involved, there's some encrypted data that goes in there, so it's a little more complicated than just that. But if you put, traditionally API gateway to Lambda DynamoDB in here, there's some consequences that go along with that when you've got another service talking to it. So you're introducing latency, right? You put API gateway up there, and that's going to cost you a couple hundred milliseconds already. You put Lambda behind it. Sometimes you can get away with API gateway with service mappings going directly to another service. But if you've got Lambda in there, you're adding another thing, especially when you've got cold starts happening in your containers. And the trick is you pay for this twice, right? For Lambda, you're paying for both an invocation, an API gateway invocation, and then the time spent in that Lambda computation. But all of that end-to-end latency you're paying for in the calling Lambda because it's taking longer, which is not true with traditional architectures. So what we choose to do is directly access the resources in other microservices. So that Lambda that's in that other service is actually given permissions to talk directly to the database, KMS, all these pieces. And I'm sure you have questions because this seems to violate separation of concerns, right? But the way that we do this is we use SDKs for our microservices. So each microservice defines an SDK that the client is using that has a simple API that replicates what it would look like on API gateway, right? The SDK for the association service is just check permission between user and robot. But it then wraps the code that checks against the resources directly, which means that our code is still well separated, that SDK is still defined with the providing microservice. So when you're looking at it from the caller's perspective, the API is just as simple. It's just not a thin wrapper around an HTTP API and sort of a thick wrapper, which means that the downside is, right, that instead of that HTTP API hiding the complexity of like your database schema, that it's still hidden in code terms, but it's now present in the client. So if I change the database schema, that means I need to update all of my callers as well. So deployments are highly coupled. And bear with me, because I understand. So we've got deployments of highly coupled microservices, right? It's just a monolith. And this is true, that we essentially deploy as a monolith. We define them as microservices, and that from a code perspective, they still exist in that modularity, but we put them up all together. And we do this primarily, again, driven by the cost. But I'm going to say that that's OK, that for various reasons, it's not so bad to have a monolith in this version as it is to have a monolith in either traditional architecture where, say, they're maybe running present on the same instances and you make assumptions about that, or that it's tied together in the code because the code is still well separated. So we've got this highly coupled deployment. So what does that actually look like if we're going to have to deploy everything all together rather than individually? So just some terminology here. I find that the terminology around how deployments gets done tends to be a little vague, and people use different terms to mean different things, or use the same terms to mean different things, or different terms to mean the same thing. In place is obviously not something that you want, where you just pull a big lever and everybody changes over all at the same time. That's a little white knuckle. So what I'll call blue-green is where your endpoint remains the same. And behind it, you're updating your instances, containers, your whatever it is. But you're rolling that out, and the client doesn't see any change in the endpoint. The other option is to do what I'll call red-black, where you're setting up a new load balancer and everything behind it, so the endpoint for the client has to change. And so we actually do this. We do red-black for our entire system. So that collection of services, we deploy the entire set again. Now, that's not true of databases that have an independent lifecycle, but for the most part, you can imagine it happening like this. And that's OK, because we're not paying for idle. That second system you stand up can just sit there for however long you want, and you're only paying for the traffic that's running through it. And this is scalable in the number of services, right? When you're deploying that, it doesn't take that much more time to deploy many services versus just one or a small number. What it's not is scalable in cadence. So when you have fully decoupled teams, right, you can have them deploy on their own schedules and not have to coordinate that. It doesn't work that way for this. If you have one version out there and you deploy a second version and you're moving all the traffic over to the second version, a third version coming in, do you move it only once they're migrated to version 2, or do you move them from version 1? It just becomes very complicated. And so we have sort of a, say at most once a day cadence, which is, not that bad, but it certainly has organizational implications as well as ops implications. So then the question becomes, all right, I've got these two endpoints that I've deployed. How do I move clients from one to the other? And this is, I talked about last time, where serverless offerings are a little lacking here. So a traditional option is to use DNS, setting aside the problem of DNS clients, which can kill this for a lot of cases. We make our robots, we control the whole stack, so we can make our DNS clients do whatever we want. Right? You've got a well-known domain name, and when the client checks for DNS, it gets a CNAME record that's pointing to your API gateway endpoint. We have API gateway at the front for facing all those services, although it's not in between each of the services. And then, when you want to switch over, you start returning different CNAME records to switch clients over. This does not work for the reason that custom domains, you can't actually put the same custom domain on two API gateways. Because of the way CloudFront works, you need the custom domain so that the TLS will work, and CloudFront uses the custom domain to determine where it's routed. And so you can't actually have two API gateways that will accept that same domain so that you can just give a CNAME to switch between them. So another option is to use a separate service that the client that has a well-known URL that you say, where should I go? And then you tell them, OK, we'll go to this one or the other one. This works better when you have multiple endpoints, because you can return a set of endpoints that are always going to be in sync. And that works for us because we have an MQTT endpoint for AWS IoT, as well as two API gateway endpoints. And I'll get to the reason for that in a second. It also helps with multi-region, right? It's the exact same model works for one versus the other. Like, the client doesn't care whether you've changed your answer because you've moved them between regions or between instances. But you have another service down here, and that you're using to help deploy another service. And so it can't just be service discovery all the way down. So we need some way for these well-known services to exist. And for that, we use CloudFront. And so here's where there's another sort of bizarre pattern, where we're putting CloudFront in front of API Gateway, which, if you're familiar with it, API Gateway uses CloudFront internally. So we're putting CloudFront in front of CloudFront. But there are two key benefits that we get out of this crazy-sounding pattern. The first is that we get that red-black switchover. So the CloudFront has an origin, and you can tell, OK, you put that one custom domain on your CloudFront distribution there, so the client is always talking to that, and then you switch the origin behind it. You can only do that, in-place update to switch all the traffic over all at once, but at least you have that well-known URL that you control. If you have multiple origins, like if you're serving static content through the same CloudFront distribution, and you're updating that, it also stays in sync. That distribution config is atomic. So all the traffic that's being routed to your new API gateway will also use those routes to your new static content origin. The other benefit is around security. So AWS WAF is a serverless web firewall that you can put on your CloudFront distributions, which is really nice. You don't have to manage your own firewall. And so then you can go in there, and it gives you insight into where your traffic's coming from. You can whitelist or blacklist IPs. We use the whitelisting approach for some low security APIs that we want to limit mostly to internal users. But there's a trick here. This breaks SIG-v4 authentication. So you can't use AWS authentication against API Gateway if you've got CloudFront in between. CloudFront modifies the host header of the traffic that goes through it, and the signature, the host header is signed, and so when it gets to API Gateway, the signature is invalid. So for that reason, we use this pattern to put WAF in front of our unauthenticated endpoints, like login APIs, but not our authenticated ones. And that's why we have those two API Gateway endpoints that we need to do discovery for. Trick here, though, is, all the traffic that's going through CloudFront you control, but API Gateway endpoints behind it are public. So it's obscured. They may not know it, but if they can figure it out, well, they can just go around it, right? So we needed a way to keep the traffic from going around the CloudFront distribution. And the way we accomplish this is with an API key. So using the custom headers in CloudFront, we drop an API key on there that API gateway will only accept traffic that has that, which means that only the traffic can go through there. And then, of course, you want to rotate this with scheduled Lambda. We do it every day. I guess if you're paranoid, you could do it every hour. You want to keep the current and the previous so that as you're switching over between endpoints, both of them work. You use usage plans to make a single key work for multiple API gateways. It's a little bit of a Rube Goldberg device, but it's working well for us. So another permissions thing, and this is sort of the flip side, is if you're going directly to resources, well, you get IAM permissions, right? You get to put policies on it that say, okay, well, this Lambda can do DynamoDB, get item on that, and maybe I could limit the keys that it's able to access. But I can't control the payload. So if there's sensitive information inside API gateway, I'm not allowed to say, scrub that out before it goes back to Lambda. Whereas if I'm going directly against an API, then there's a Lambda in between that can say, oh, don't actually give them back that. And then you still have the IAM policies that allow you to control whether that API is even callable in the first place. We use sort of a system where the microservices define what resources they expose, and other services define what they require, and then we auto-generate those IAM policies based on that, so it's always least privilege. For us, because we're not going through API gateway, for systems patterns like this, we go direct to another Lambda, so only that Lambda would have permission to the DynamoDB, and the calling Lambda would have access to invoke this other Lambda. We don't find that that comes up often, but there are certain cases where it might be necessary, especially if you have encrypted data inside there and you don't actually want to expose the key, because for some reason that key is also sensitive within your organization. So to sum up this part, I'm going much quicker than I expected. It's good, we're making up time. We have microservices that are directly accessing each other's resources, and this is sort of contrary to how microservices traditionally operate. This is driven by cost. This causes us to have to do certain patterns in our deployments, and we use red-black across our entire application for that. And we also use CloudFront with WAF in front of API Gateway as another pattern. And this has impacts on cost, latency, deployment, discovery, and security. So the second part of my talk is just basically a soapbox that I'd like to talk about a few things in serverless that I'd like to address. First, serverless sort of as an identity for a system. A few things about testing, and what I think is missing from serverless providers today. So first, serverless is not binary. So I work in cloud robotics, and I get a question a lot from roboticists, like how is that different from networked robotics, which is something that's been around for 3 decades. And the answer is fundamentally it's not. But with increasing scale, right? Both of them are about using connected robots, like connecting robots to enable them to do more and better things. But as you scale both the number of robots and the connectivity of each robot and the computing power behind it, you end up needing different techniques to address the problems that you want to solve. In a similar way, serverless isn't binary. It's a spectrum, right? And so, I heard somebody say recently, oh, DynamoDB isn't serverless because you have to provision throughput. And I don't think that's true. It's less serverless than if you didn't have to provision throughput. I would say that services that use managed instances, the less you have to manage the instance, the more serverless it is. So something like Redshift, where, well, you got to define the size of the cluster, but you're not doing, security patching or managing really the instances themselves, is, fairly serverless. But Google's BigQuery, which provides the same service but doesn't require provisioning, is more of a serverless offering. And so it's really about how much effort is it to provision and scale the service. So on testing, for unit testing, one of the things that came up recently, I don't think there's a need for abstraction layers inside your functions. if you've really modularized them well, the happy path where it's interacting with other services should be like 5 or 10 lines of code, right? Whatever the internal logic of your function is going to be however big you want it to be. But and with error handling, you may get 5 or 10x the happy path. But really, if you're touching a couple of other services, it should really be pretty short. And so I don't think you actually need to abstract that. What I'd say is instead mock the SDK calls that you're using. And on AWS, there are facilities for this. We're in Python, we use Placebo. There are ones for Node as well. And one of the benefits we get there, so these are libraries where you make regular SDK calls and you sort of record it to a file. It instruments the SDK. And then for testing, you play back from that file. And so when the function makes an SDK call, it will get intercepted and just return what the file produces. And so we use that, and this microservice SDK system that we use, we get that for free because they're just making SDK calls under the hood. They're not talking to an HTTP layer that we have to mock separately. Another piece here is unit testing versus integration testing. So they're both important. You can unit test, but integration testing may not. May show that you may have mistaken. So my assertion is that you can't do this locally, that you shouldn't try to do it locally. If you're just API Gateway, Lambda, and DynamoDB, like sure, use DynamoDB local, but if you're anything more complicated than that, just deploy it. It's going to be better in the long term anyway. There are some projects that try and mock a wide range of, say, AWS services. They're never complete. They're never going to have all the features you want, and your testing infrastructure should not limit the features that you're using from the services. And so for us, what this has meant is that once we're deployed, we want to test all these services that we're using. But you can't make DynamoDB act badly. And you can't make, if you've got an S3 bucket notification that feeds into SNS, you can't pretend that SNS is down. So what does that even look like, right? If you don't know what the log messages look like when that's happening, you can't be sure that you'll know that it's happening if it happens. And so the approach that we take is we use that SDK mocking to inject errors that we would see. And so both, right, mocking out, oh, DynamoDB is unavailable, it just returns 500s. Or, say DynamoDB says 404 for a resource that's actually present. Or it returns 500 but has actually written the record. Or it's just got high latency, so wait a second before writing it. Or write it and then wait a second. And so we have that between our Lambdas and every services that they touch. That allows us to at least see both how our system degrades and then also simulate situations so that we can make sure that we're monitoring correctly. So I want to talk about what's still missing. At the last Serverlessconf, I talked a bit about what I thought was missing from deployment tooling and reasons that we ended up rolling our own. And that's come a long ways. I think both the serverless framework, which has gone out of beta, and there's projects like Go Sparta, and Flourish is sort of percolating. I don't know what the word is. Hopefully it will bubble up to the surface eventually. First thing that I want is Lambda environment variables. So this is provider stuff, right? What can providers do to make our lives easier? So right now, when we deploy a set of services together, we don't have any way out of the box to tell Lambda what DynamoDB table to use. And so we do this with a CloudFormation custom resource that basically takes the source, unzips it, drops a file in with the data that we want, zips it back up and deploys it. That'd be really nice if that was built in, because then it would be inspectable. You could look and ask the Lambda function, what does it say inside this? And then you could be sure, whereas right now we're just trusting that our logic has done the correct thing and that nobody has mucked around with it in between. I really want that. The other thing I want, that's deployment time, right? If I know the DynamoDB table inside a microservice, the Lambda inside that microservice can know. But if I'm doing that thing where I'm allowing access to that table from outside a service, this applies even if you've got API gateway fronting all of your microservices. How do you know what that API gateway endpoint is? Because it's auto-generated between the different services that you use. You only know that at runtime. And so what I want is service discovery. I want some way of telling these at runtime, looking up what they need to use. We currently do that by having like a DynamoDB table with a well-known name that we're injecting across our application in those environment variables that then get populated by other CloudFormation custom resources that drop the requisite names in. But that's like we've built that and are making sure it works, and we don't want to do that. So something that's service discovery that, if I could put all of my services with VPC endpoints so I could seal my Lambdas off, I could run console inside that VPC and maybe do it that way. But that's like, I want to seal all of my services off inside Lambda, but that's all of AWS working together to provide us that. Service discovery as a service could be IAM-based, where based on who you are, there's a service that will return different values for just keys. That would work great. Yeah, and so that's something that I see missing across of all functions as a service offerings, is a way to really at runtime stitch things together. So another thing that I would want, and this is more of a security piece, is some sort of hash-based or e-tagging of Lambdas based on just the content that's inside of it. So take the source code that's going in, and if I had environment variables, that would go in the hash too, not the things that I can change after I deploy it. But so I can predict that, so the SecOps team can look at the repo and say, this is what's supposed to be deployed, I know what that hash is, and make sure that what's running on Lambda is exactly what we want it to be. Because otherwise, if you're not watching CloudTrail closely enough, someone could go in there and insert something into your Lambda, and until I can seal that off in a VPC, that could include calling out to who knows where. And then deployment. So all of these things that I talked about where have a separate service discovery service for clients, and we're trying to do these red-black things behind CloudFront and all of these things, is because basically like API Gateway and Lambda don't support doing incremental rollouts as sort of a fundamental part of the service. And I had some crazy ideas about how this might work that I had on the plane and I wrote up, so I'm just going to throw that out there. So imagine we have two stages. There's a red and a black stage. And imagine that these are different deployments, but they're not like different versions of your API. You're still on V1 of your API, so just to make that clear. And so one thing that I actually really like about Azure Functions over Lambda is that the stage is a subdomain rather than in the path, which means that theoretically you could like CNAME across that rather than having to update the path that the client is using. But given that we use Lambda and like it for many other reasons, you've got this path where it's red, V1, whatever. And then to switch to this other stage, you have to say, okay, here's this different path that you have to go to, or here's a different URL you have to go to. But what if instead you had some sort of third stage that was different from those other two? You define it differently, and say it's called prod, and so you get this well-known URL that you get to go to, and inside that, there's a Lambda that's calling out, and it works maybe like a custom authorizer, where you say, when I get called this, provide me with like the headers that are coming in and the path, and I'll return to you a stage name. And so I say, here's, I've gotten this, I saw this client ID, so I'm going to say red, and I'm going to say TTL of 5 minutes. And so it'll just do what amounts to path rewriting to send you over to the red stage. Doesn't do any interpretation on the path, none of that. Just basically proxying over. And so once I've deployed, my black deployment, and I want to switch over there, well, then I tell that Lambda, okay, well, now send 10% randomly over to that. And so it's sticky with some header that you define, right? And we'll say, okay, this client I've selected to be one of, A/B tested against this. So I'm going to send them over to the black one, but I'm going to give that a TTL of something else. So this would allow us to do within the existing sort of setup, a way to have a single stage that you're not updating in place and switching all the traffic over at once. So I think this could be a solution. I mean, ideally, you'd have sort of version choosers, like you'd have some managed way of saying 10% of the traffic, but I'm more than willing to implement that myself if I have the ability to reuse the same API gateway. So to sum up here, our architecture skips API gateway in between our microservices. And this has a lot of implications across our architecture. And it's both pro and con, right? It's not something that I would necessarily recommend. But if your primary driver is cost, like it is for us, where we measure it in pennies per robot over their lifetime, this, I think, is a good choice. For security, we put CloudFront WAF in front of API Gateway. It's kind of complicated, but until you can put WAF directly on API Gateway and it works with SIG-v4 authentication, we're kind of stuck with it. And then finally, these pieces that serverless is a spectrum, that it's not, are there servers, are there not? It's, how much easier on the spectrum of both development and operations is it, according to, the ideas that are contained in serverless. And finally, only do your integration testing on deployed systems, and we should get better deployment models so that doing that integration testing is easier. So now I'll open up for questions. I think if we only take 5 minutes, we will be ahead of time. Yeah? Yeah, so I pulled that off of a website that was comparing it for EC2. So you have to take that sort of as a, we haven't measured this directly. We know that
just wanted to take a picture.
Sorry.
That's it.
There we go. The URL is down at the bottom.
Anybody else?
Yeah.
So if you're deploying with
Can I just pass it
switching the origin in CloudFormation, do you get any problems with the time it takes, especially if you have to roll back or something, or is it just in your process and you know it's going to work?
So the amount of time it takes for all the distributions to update, I believe the way it works is they all communicate the new distribution config before they start switching. And so you don't see like a sort of wave of rollouts across the POPs. But it doesn't really matter to us because it's an in-place update anyway. We don't have much control over whether it takes a minute or an hour. And so as long as it's atomic, everything in that distribution config is true for any given traffic that's going through it. So some traffic that's going through a given instance inside of a CloudFront data center is not routing it to this origin, but not putting the appropriate header on it. As long as that doesn't happen, we're sort of fine with any behavior.
You mentioned mocking bad behaviors from AWS services. Can you talk a little bit about how you develop your collection of bad behaviors and how complex those behaviors are?
So the question is about how we mock bad behaviors of AWS services. So because we're using Placebo, Bodo Core has all of the definitions for all of the errors. And so it's pretty easy to just say, return throttling exception and have all of that auto-generated for you. We have a little specification language for the latency and the randomness and stuff, but it's all relatively straightforward, right? Just having those Bodo Core definitions gets us like 90% of the way.
So we are pretty much running out of time. If there are more questions, maybe Ben, if you can hang around afterwards,
yeah,
maybe people can ask. If you'll join me in thanking Ben for the conversation we had this morning.